Good morning to one and all. Today's topic is properties of continuous functions. Sign preserving property. The statement is as follows. If f of x is continuous at a point A and f of A not equal to 0, then there exists delta greater than 0 such that f of x has same sign as f of A in the neighborhood of A, that is A minus delta comma A plus delta. Observe the statement. F of x is continuous at a point A. That means limit x tends to A, f of x equal to f of A, and also given that f of A not equal to 0. These two are given concepts. Now we want to prove that there exists delta greater than 0 such that f of A and f of x will have same sign in the neighborhood A minus delta and A plus delta. So we want to prove this. F of x and f of A will have same sign means if f of x is positive, f of A is also positive. If f of x is negative, f of A is also negative. So what is f of x? What is f of A? F of x means x may be any one of the point of this open interval. If the value of f at these points is positive, the value of f at A is also positive. If the value of f at these points is negative, the value of f at A is also negative. Neighborhood means consider take A as 7, then open interval is 6, 8. Now we can say that the open interval 6, 8 is the neighborhood of 7. In this neighborhood, the points between 6 and 8 will exist, but 6 and 8 are not existing. Proof. By data, f of x is continuous at a point x equal to A. That means limit x tends to A, f of x equal to f of A. Then by the definition of continuity of a function, we have for each epsilon greater than 0, there exists delta greater than 0 such that modulus of f of x minus f of A less than epsilon whenever modulus of x minus A less than delta. Here we have modulus of f of x minus f of A less than epsilon. So whenever we have this step, they can easily write minus epsilon less than f of x minus f of A less than epsilon. Take this minus f of A to this side, f of A minus epsilon less than f of x less than f of A plus epsilon. That means negative f of A goes to this side and this side. Then we are going to get positive f of A minus epsilon less than f of x less than f of A plus epsilon. In the similar manner, modulus of x minus A less than delta implies negative of delta less than x minus A less than positive delta. Minus a goes to this side, then becomes positive. Minus a goes to this side, then it also becomes positive. So now we have f of a minus epsilon less than f of x less than f of a plus epsilon for a minus delta less than x less than a plus delta. Take this as equation 1. By data, f of a not equal to 0. That means f of a less than 0 or f of a greater than 0. F of a less than 0 means it is negative. F of a greater than 0 means it is positive. If f of a is negative, then modulus of f of a equal to modulus of negative quantity, that is positive. Positive means greater than 0. F of a is positive. Modulus of f of a equal to modulus of positive. Modulus of positive quantity is positive, which is greater than 0. So, in both the cases, modulus of f of a is greater than 0. Observe, f of a not equal to 0 implies modulus of f of a is greater than 0. Choose epsilon less than modulus of f of a. In this situation, f of a minus epsilon and f of a plus epsilon both have same sign as f of a. Observe, here I am taking example. If f of a is positive, negative, that's why we are taking f of a as minus 5. Modulus of f of a equal to modulus of minus 5, that is 5. So, mod f of a value is 5. Substitute here. Epsilon less than 5 implies I am taking epsilon as 3. 3 less than 5 is true. Now we have f of a will have value minus 5. Epsilon will have value 3. Now I am going to find out f of a plus epsilon, that is minus 5 plus 3, that is minus 2, less than 0. F of a minus epsilon equal to minus 5. Epsilon is 3 minus 3. Minus 5 minus 3 is minus 8. That is less than 0. Observe, f of a negative, f of a plus epsilon negative, f of a minus epsilon is negative. That means these three will have same sign. Now we are taking f of a as positive. Epsilon less than modulus of f of a implies modulus of 7 is, I am writing here. So I am taking epsilon as 5. 5 is less than 7 is true. So f of a is 7. Epsilon is 5. F of a minus epsilon equal to 7 minus 5 is 2. F of a plus epsilon means 7 plus 5 is 12. This is greater than 0. This is also greater than 0. F of a is also greater than 0. So these three quantities will have same sign. Already we have equation 1. This is equation 1. Observe, here f of a minus epsilon positive, f of a plus epsilon is positive. In between two positive quantities, we have only positive quantity. That's why f of x is positive. But whenever this is positive means f of a is also positive. Therefore, f of x and f of a will have same sign. In the case of negative, that is this previous case, f of a minus epsilon is negative, f of a plus epsilon is negative, f of a is also negative. In between two negative quantities, we have one more negative quantity. That's why f of x and f of a will have same sign. So, the theorem is proved. Next theorem, location of roots property. If f of x is continuous in a closed interval a comma b and f of a and f of b are of opposite signs, then f of x vanishes for at least one value of x equal to c belongs to closed interval a comma b, that is f of c equal to 0. So, go through the statement. F of x is continuous in a closed interval a comma b. That means f of x is continuous at each and every point of this closed interval. F of a and f of b are of opposite signs. That means if f of a greater than 0, f of b less than 0. If f of a less than 0, then f of b greater than 0. In this situation, f of a and f of b are of opposite signs. In this situation also, f of a and f of b are of opposite signs. Now we have to prove that f of x vanishes for at least one value of x equal to c belongs to closed interval a comma b. Assume this is x equal to c belongs to closed interval a comma b. At this point, the value of the function is 0. Vanishes means it equals to 0. Now we want to prove this one. So, proof. By data, f of a and f of b are of opposite signs. We shall assume f of a less than 0 and f of b greater than 0. So, we are going to prove theorem for this case. Consider the subset S of closed interval a comma b. Observe, if the closed interval a comma b points are in this set, then subset means some points of closed interval a comma b. Otherwise, if you take closed interval like this, then subset of closed interval a comma b means set of some points of closed interval a comma b. This is the set S. In this set, the elements must satisfy one condition, that is f of x is less than 0. Whenever the value of f at this particular point is less than 0, then this point belongs to S. And also find the value of f at this point. If it is also less than 0, then this point belongs to S. From this, what we are going to understand, any point in S must satisfy f of x less than 0. Now, S is not empty. Why means, here we have one condition. What is that one? F of a less than 0. So, a is an element of S. If one element is existing in S means it is a non-empty set. Consider closed interval a comma b. S is subset of closed interval a comma b. That means S contains some points of closed interval a comma b. If we take like this, a comma b is closed interval, S is subset of this closed interval. Okay, now the points of S must satisfy the condition, that is f of x is less than 0. This S set is not empty. Y means f of a is less than 0. So observe, f of a less than 0, f of x is less than 0. Whenever this condition is true, x is a point in S. The similar condition we have, that is f of a is less than 0. So a is a point in S. From this concept, we know that a is an element of S. Therefore, S is not empty. Now the set S is bounded because S is the subset of closed interval. This closed interval is bounded. That's why automatically S is bounded. Let bounded means it is both bounded above and bounded below. So S is bounded above and bounded below. Whenever S is bounded above, compulsory least upper bound will exist. Take that least upper bound as C. Now there are three possibilities we have. First one is the value of f at C greater than 0, the value of f at C less than 0, the value of C equal to 0. So here we are taking C is the least upper bound of S. That means C is the least quantity when we form upper bounds set. Observe, if this is upper bound set of S, in this set C is the least. The number less than C cannot be upper bound. That means C minus epsilon cannot be an upper bound. And also upper bound, from the definition of upper bound, we can say that f of x is always less than or equal to C. And also f of x is greater than C minus epsilon. Suppose f of c greater than 0, then what will happen? Then there exists a neighborhood c minus delta 1, comma c plus delta 1 of c such that f of x is greater than 0. This line is basing on previous theorem. There, instead of c, we have a. In that theorem, we proved f of a and f of x will have same sign. By using that theorem, we can easily say that f of c and f of x will have same sign in this neighborhood. But the points of S satisfy the condition f of x less than 0. But here we have f of x greater than 0. That means no point of S can be in this neighborhood. So the points of S does not belongs to in this neighborhood. That is, once I am writing this neighborhood, so write down the neighborhood c minus delta 1, c plus delta 1. So the points of S does not belongs to this neighborhood because in this neighborhood f of x value greater than 0. That is, every point of S either less than or equal to c minus delta 1 or greater than or equal to c plus delta 1. So, between these two points, that is c minus delta 1 and c plus delta 1, these points does not belongs to S. The points of S may be less than or equal to c minus delta 1, that means this left side, or the points of S are greater than or equal to c plus delta 1. Since c is an upper bound of S, c is least upper bound of S, the latter situation cannot arise. So once again, c is an upper bound of S. That means f of x values is always less than or equal to c. Here the points are greater than c. That's why this situation cannot arise. Once again, since c is an upper bound of S, that means the values of f at x are always less than or equal to c. So here the points are more than c. That's why this situation cannot arise. That means the points of S are belongs to or less than or equal to c minus delta 1. Thus c minus delta 1, we already know c minus something means which is less than c, is an upper bound of S. So c minus delta 1 means c minus something means this is compulsory less than c. Whenever this situation is true means f of x is less than or equal to c minus delta 1. That means here we are taking c as least upper bound. Whenever this is least, the number which is less than c cannot be satisfy this condition. This contradicts the fact that c is the least upper bound for S. Therefore, f of c greater than 0 is not possible. Once again, from here onwards, I will explain once again. Suppose f of c greater than 0. Then there exists a neighborhood c minus delta 1 comma c plus delta 1 of c such that f of x greater than 0. This is basing on previous theorem. F of c and f of x will have same sign. So the points of S must satisfy the condition f of x less than 0. But here we have f of x greater than 0. That means the points of S does not belongs to this open interval. So the points of S may be less than or equal to c minus delta 1 this side or greater than or equal to c plus delta 1. Since c is upper bound of S, upper bound means f of x values less than or equal to c. In this region, we have more than c. In this case, we get the points more than c. That's why the latter situation cannot arise. So, the only possibility is f of x values are less than or equal to c minus delta 1. That means this side. We already taken c as least upper bound. That means in this upper bound set, c is the least. So the numbers less than c cannot be upper bound of f of x. Therefore, this situation is also not arise. Therefore, f of c greater than 0 is not possible. Next we are considering f of c less than 0. Why means before we taken greater than 0, now we have taken less than 0. Again basing on previous theorem, f of c less than 0 means f of x is also less than 0. In open interval, neighborhood means open interval only, c minus delta 2 comma c plus delta 2. Both f of c and f of x will have same sign. So in this open interval, the values of f are less than 0. In particular, I am taking the open interval c, c plus delta 2. In total open interval f of x is less than 0 means in this region also f of x is less than 0. So again the same concept we are using. C is an upper bound of s means f of x is less than or equal to c. Here we have the points more than c. That's why this is also not possible. Therefore, f of c is less than 0 is not possible. So, we have three options. In three options, f of c greater than 0 is not possible. F of c less than 0 is not possible. So, remaining option is f of c equal to 0. Next, we are considering closed interval. C may be equal to a. So, c equal to a. At that situation, f of c equal to f of a. But from our assumption, f of a is less than 0. So, f of a less than 0. Therefore, f of c is less than 0. If f of c equal to b, then f of c equal to f of b. Again by our assumption, f of b greater than 0. Therefore, f of c is greater than 0. These two are not possible. That means c value not equal to a, c value not equal to b. So, c lies in between a and b. Therefore, location of roots theorem is proved.